Good morning, 8th graders. Hope you're doing well. We're starting on a new unit today in science with forces and motion. And so we're going to go into some fun things that'll include some fun labs that you can do at home of testing out speed and arc and energy distribution. So it'll be fun. But we're going to start on 4.1.1 and read that chapter together and go over the questions. So we're on page 196 on 4.1.1, and we're starting with forces. Have you ever played baseball, football, or hockey? Have you ever pulled weeds, swept the floor, or shoveled snow? Have you ever tugged on the leash of an unwilling dog, trying to get it to follow you? These actions all involve force. Other examples include picking up a book, throwing a frisbee, riding a bike, and shooting a rubber band across the room. A force is a push or pull exerted on an object. For example, an engine pushes a rocket through space. A magnet pulls on metal filings. The moon pulls on the ocean to create tides. A negatively charged particle repels another negatively charged particle. A potter pushes and pulls a lump of clay to form a bowl. The amount of force applied to an object is measured in units called newtons, or capital N. In honor of Sir Isaac Newton, 1 newton is the force exerted by Earth's gravity on an object that has a mass of 100 grams, the mass of a typical apple. A Newton spring scale is commonly used to measure the force exerted on something. When you think about pushing or pulling an object, you usually think of applying force by touching something. When you push a door open, for example, your body has to come in contact with the door. Forces that require contact between two objects or substances is called contact forces. So that's pretty self-explanatory. You have to touch it in order to cause that force to happen. Several kinds of contact forces are at work on Earth. Each one affects how people, animals, and objects interact with the world. For instance, buoyant force is upward force exerted on an object in a fluid. This force keeps ice cubes floating at the top of water in a glass. So if you've ever tried to push a pool noodle under the water or a floaty under the water, it bounces right back up depending on the amount of force. If it's really buoyant, then it's going to be really hard to push it under. Elastic force pulls a stretched object back to its regular shape. It's at work in a bungee cord that straps a bicycle to the car. The cord stretches when the car goes over a bump, but immediately returns to its original shape and keeps your bicycle from falling off the car. Okay, same thing with if you were hanging from a bungee cord. If you were to let go, it would spring back. Let's see. Tensile force results in a pull exerted on an object. For example, a tensile force is exerted during a tug-of-war game. So you've got opposing strength pulling against each other. Other contact forces include compressional force, shearing force, and friction. Compressional force results from pushing or squeezing an object, so like compressing it. Gas is compressed to fit into a propane tank. Shearing force is sliding force. When it is great enough, the force can break an object apart. Scissors, also known as shears, exert this kind of force. So you have two blades that are rubbing against each other and causing that force to be able to cut through things. Friction is a force that resists motion in objects that are moving against each other. Friction keeps a car from sliding across dry pavement the way it slides across ice. It also prevents an object from sliding easily across a carpet. Also with friction, if you think of like a balloon and you rub it and it causes that friction from rubbing together and it causes something called static electricity and holds it to your head. But that friction is force when you're rubbing two things together, and typically, the result of that is heat. Not all forces in creation require contact between two objects. The forces that do not require contact are called non-contact forces. These forces are also called the fundamental forces, because all forces are the result of these fundamental forces. They play a very important part in the universe. The four fundamental forces are gravitational force, or gravity, electromagnetic force, weak nuclear force, and strong nuclear force. Gravitational force is an obvious part of life. When a ball is thrown straight up in the air, arm muscles provide a push that sends the ball into the sky. Eventually, however, the ball changes direction as the force of gravity pulls it back to the earth. The ball does not need to be in contact with anything to be affected by gravity. Gravity not only pulls things to the Earth's surface, but it also is a force of attraction between any two objects. All objects with mass, not just Earth, exert gravitational force on objects around them. In fact, you are actually exerting gravitational force on the Earth, even as if you were exerting gravitational force on you. The amount of gravity that an object exerts depends on the mass of the object and its distance from the other object. The more massive an object, the greater its gravitational pull, and the smaller the distance between objects, the greater the gravitational pull. The force that a desk exerts on its user is small compared with the force the Earth exerts on you, because the desk has much less mass than the Earth. So if you think of planets and moons are usually held onto the orbit of a planet because of gravitational force. It gets caught in its gravitational sphere and stays within orbit. And so the closer the moon, or closer an asteroid or a satellite is to a planet, the stronger that gravitational force. Same thing with, if you're on the surface of the Earth, the gravitational force is going to be stronger to keep you grounded to the Earth than as you go higher into the atmosphere and out into space where there's much less or no gravity. And so the closer objects are together, the stronger the gravitational force. On the side there, you have laws and principles. Weight versus mass. Often science experiments call for measuring a few grams of this and a few grams of that. A gram is a unit of mass. Weight is a measure of the force of gravity acting on that mass. The unit for weight is Newton, not the gram. The formula, F equals m times g, is used to convert mass to weight. F is the force of gravity in newtons, the letter m is the mass of the object in kilograms, and g is the acceleration of gravity, which is 9.8 meters per second squared. If an object has a mass of 30 kilograms, the gravitational force, or weight, would be solved as follows. 30 kilograms times 9.8 meters per second squared equals 294 newtons. The second fundamental force is electromagnetic force. Electric and magnetic forces interact with each other so closely that physicists consider these forces as a single force. The electromagnetic non-contact force is much stronger than gravity. It determines the ways in which electrical charged particles interact with each other and with magnetic fields. It can attract or repel. The electromagnetic force binds atoms together by holding electrons in their orbit around a positively charged nucleus. And so you see this a lot in science. There's actually, I went to a planetarium in Florida this past winter, and they had a video in their planetarium about electromagnetism and creating mass out of electrons. And so there's this huge, I forget what it's called, like a supercharged something in Switzerland, and it's miles and miles underground, and it's a big tunnel system. And what it does is it has conductors that have positive and negatively charged electron particles, protons, neutrons, and it shoots them through this tunnel, and they move at a rapid pace, and where they collide, their calculating the energy, the amount of energy that is created from those electrons colliding. I'll see if I can find a link on it to send you guys to watch. But that electromagnetic force is actually stronger than gravitational pull, is what that's saying. Science in action, up at the top in the gray box. Change in force. When determining the gravitational force between two objects, mass and distance are needed to be considered. The greater the mass, the greater the force. The smaller the distance, the greater the force. These facts can be used to determine a change in force in a given system. Suppose two objects are 12 meters apart and they are moved only 3 meters apart. How does that force change? To solve, take the factor needed to change 12 to 3, a quarter. Then invert the factor and square it. 4 squared, which is 16. The gravitational force has increased 16 times by the factor of 16. Consider the mass of two objects exerting force on each other. The mass of object 1 is 8 kilograms. The mass of object 2 is 24 kilograms. Replace object 1 with an object that has a mass of 32 kilograms. Determine what factor is needed to change 8 to 32 kilograms. The change means the gravitational force has increased 4 times or by a factor of 4. What happens if the secondary object is changed as well? If the secondary object is replaced with a 72 kilogram object, the force will increase by a factor of 3. What happens if all 3 changes are made? All the factors are multiplied together, 16 times 4 times 3, which is 192. With all these changes, the gravitational force increases by a factor of 192. The strength of the magnetic force, like that of gravity, also depends on the distance between objects. The closer together the objects, the stronger the force. The farther apart, the weaker the force. If you think of magnets, if you hold a positive and a negatively charged magnet apart, they're not attracted to each other. But the closer you get, and depending on how strong those magnets are, they're eventually going to stick together pretty strong, stronger than you can hold them apart. But the farther away you go, the less that force or the less that attraction is. 2 more fundamental forces work inside the atom to contribute to its stability. One is called the weak nuclear force, which is the force within the atomic nucleus that is responsible for certain types of radioactivity. It is what prompts the nuclear fusion reaction that fuels the sun. The other, a powerful attractive force called the strong nuclear force, and it's the strongest of the 4 basic non-contact forces. It holds the protons and neutrons in the nucleus of the atom and overcomes the repulsion between the protons as a result of electromagnetic forces. So I'll read that again. It holds the protons and neutrons in the nucleus of the atom and overcomes the repulsion between protons as a result of the electromagnetic force. So this force, the stronger nuclear force, is what holds protons and neutrons in the nucleus together, so they're not being repelled to each other. Under certain conditions, the nucleus of an atom can be blown apart by neutrons fired at it. Splitting the nucleus of an atom is called nuclear fission. During nuclear fission, the very powerful nuclear force is overcome and incredibly huge amounts of energy are released. Physicists have used that energy constructively in nuclear power plants and destructively in nuclear weapons. And this is what I was talking about with that science place lab in Switzerland, where they're, shooting atoms at rapid speeds and crashing them together to split the nucleus of an atom to create energy. All right, questions for today. What is force? Find the definition of that. What is the difference between contact force and a non-contact force? Describe elastic force and compressional force. Give an example of each. So elastic force and compressional force. Give an example of each. What of the 4 fundamental forces? These were the last ones that we read about. Are these contact or non-contact forces? Do you need to be pushing or pulling or doing something to it in order for them to take place, or do they happen naturally without needing contact? What affects the strength of gravitational force? And calculate the gravitational force on an object that has a mass of 82 kilograms. So go back and look at that formula for the gravitational force of an object. So you've changed in force, and see if you can do that. And we can go over answers on that if you have any questions. In your lab book, there are a couple labs that if you have the materials for, you can try. On 4.1.1a, it's elastic force. So you would need a rubber band, a stand with a clamp or something to hook the rubber band to, a metric ruler, and several different household or hooked masses. So things that you can attach to it, okay? And what you're going to be doing is figuring out how mass is related to electric force, okay? Or elastic force, excuse me. And so what this lab would look like is hang the rubber band on the clamp, measure the length of the rubber band and record it, attach the smallest mass to the end of the rubber band, measure the length of the rubber band and record it in the data table once it's attached. So what you could do is maybe find some objects and attach them to an elastic band with a paper clip, if that's possible, and hang it from it, and then measure what is the elastic first at resting without anything attached to it, then put the mass hanging on it, and then measure how long did it stretch, okay? Remove the mass and allow the elastic force to reshape the rubber band. Repeat the above procedure with other masses. Plot the relationship between the mass and the length of the rubber band on the graph. So you're going to be creating like a line graph or a plot graph where you can kind of show the change in mass compared to elastic, the length of the elastic band. For lab B, for friction, which surface provides the greatest frictional force? This one you're probably not going to be able to do unless you have a Newton spring scale. So unless you have a Newton spring scale hanging around your house, don't worry about doing that lab. Next time, we're going to be going on to reading about motion. So do your best today thinking about forces of what am I trying to say? Forces in general. So things that you do throughout the day that need or require force. Obviously, gravitational pull is a force that's on us every day. So we're experiencing that whether we want to or not. But think of some things that you're doing throughout the day and what kind of force that uses. Are you pushing? Are you pulling? Are things being drawn together or apart? And just start thinking scientifically about that because we're living science every day without even knowing it. So enjoy the rest of your day on that. I'll see if I can find some videos on that science lab in Switzerland and send them along. Have a great day, and I will see you next time.